Welcome to lecture 23. We're talking about energy storage today. All right, in this first video, we're just going to motivate again what energy storage is for and talk a little bit about some of the technology. So in lecture 22, I showed this plot we're looking at here where we have on the bottom the time of day, and then here we have the energy demand on the system. And this plot's been organized according to how we're generating that power. On the bottom is our base load generation, our large power plants that we never turn off, that are highly efficient, and that are always generating power. Next is our mid-merit generation, which is kind of our daytime power. We turn them on when the morning begins and kind of turn them off once the evening is over. And then peaking generation is for when everyone comes home and turns everything on at about 5 to 7 p.m. We don't turn these on very much. They're usually small, not very efficient. So this kind of load curve we look at, the energy demand in this blue curve we see, since it's highly variable and we've created all these different types of power plants to meet this variable demand, we sometimes have inefficiencies in the system, especially here during peaking hours. And so what we want to do is something called load balancing, where we are trying to offset the sudden spikes in the load by doing something to meet that demand without maybe having to generate power at that exact moment. Likewise, not just looking at the current electricity load, but also renewable energy. Renewable energy has a variable energy output, which tends to peak here in the midday if we're talking about solar, or in the morning and evening if we're talking about wind, depending on where you are. And so since looking at a large renewable adoption, we're going to have to find a way to take the extreme peak in power generation. We will see that will be our new generation curve. We need to take that and flatten it out, balance that with the load. So the way we are going to do that is with energy storage. Energy storage is the key. Okay, and the way it's depicted in this plot is our load is below the ability of the base load to generate power. And so in this plot, actually, this excess energy generated by the base load, which we never want to turn the base off, the base power plants off. So instead we store that in some sort of technology. And then when we reach a point where we have a sudden spike in power, we, instead of turning on these peaking plants, we take energy from our storage and use it to meet that demand. So this is the idea behind energy storage, is load balancing and also adjusting to a grid with high renewable energy penetration. Okay, let's look a little bit more at renewable energy and why we might need some storage. Okay, so this right here is our load in California, I believe. And you see we have it changing with year. So here we've got the load in 2012. And then as we increase the penetration of renewables, so with each year we increase the renewable mix, how many renewables we have in our total generation ability. And since our solar is going to peak in its generation at about noon or a little after, then the total amount of power that we have to generate is dropping significantly. Eventually we reach a point where, say this is the base load, we're going to drop below the base load, and we now have something called overgeneration, where we are making too much power, right? And so this, famously called the duck curve, shows how storage could be used here. So during these times when we have a high output of solar, we store that energy now in some storage medium. Then when solar drops off right here, but our demand increases significantly in the early afternoon, late evening, then without storage, we have this sudden huge increase in power that we must generate by turning on all kinds of power plants at once, undoubtedly an inefficient process. if instead we can use the massive amount of energy we stored from the excess solar to meet that increased demand, that would be ideal. So that's the motivation for storage, why we need it. So let's talk about some of the storage technologies that we have already and in fact use now. Okay, the most popular and my personal favorite is of course pumped hydro storage. This we will talk about in more detail in video number 2 of this lecture. In brief, we pump water uphill when we have an excess of energy. So we had excess energy, we needed a way to store it. What we did was we stored it as gravitational potential energy. We took a weight and we lifted it off the ground and we allowed it to stay higher above the ground. That weight was water. We use water because it's easy to move and we have technology to move it efficiently, a pump. Then, once we need that stored gravitational energy, we allow that weight to fall, and we allow it to fall through a turbine, which the water spins and we generate power. So we've just stored gravitational energy. Okay, so that's pumped hydro storage. We also have batteries. So a battery is direct conversion of chemical energy into electrical energy. We're going to talk more about these in our 3rd video. They utilize things called redox reactions. It does this through the separation of electrons and ions. Okay, these are a little bit different from a fuel cell. A fuel cell, like a battery, is the direct conversion of chemical energy into electrical energy. However, instead of using the actual battery as the storage of the chemical that is converted, instead, what's different is it uses a fuel plus an oxidation source. So a battery is kind of a standalone device. A fuel cell takes in fuel and usually oxygen or water or something like that and creates electricity from a reaction. Another interesting technology, usually kind of used for vehicles and less large-term energy storage, is a flywheel, which converts rotational energy, or we could say kinetic energy, into electrical. And this really is just a very large weight, which we use a motor to spin, and it's got a significant amount of rotational momentum so that it will continue spinning, storing that kinetic energy, and we minimize the rotational losses as much as possible. Then when we need to extract energy, this is also connected to a generator. So when we need to extract energy, we turn on this generator and allow this rotational momentum to generate electricity, which will slow down this rotating weight. Okay, this plot right here shows how the different technologies compare currently with respect to how much energy we can store and then the maximum power output we can get from this technology. So here we've got megawatt hours of energy stored, and notice it is a log scale, which means going to the right doesn't mean you're linearly increasing your ability, you're exponentially increasing your ability to hold energy. Likewise, this is a log scale as well. And I will note that this is also a log scale, which means as we go up, we exponentially increase our ability to extract that energy at a certain rate. Okay, now since we have total energy, and if we divide that by the amount of power, then we find how long it takes to actually exhaust our energy storage, given as these dotted lines, which here is 3 seconds, 1 hour, and 41 days. All right, so let's look at it. Here we've got electrochemical batteries, the kind of batteries you're used to. And you see they don't actually store that much energy. They don't give you that much power, and they last for an hour or maybe more, depending on how good your battery is. Likewise, flywheels fall in this kind of low energy storage, but they're actually pretty good at extracting that energy at a given rate. But they don't last very long, maybe 3-4 seconds, depending on how much power you need to extract. Okay, the real kings are up here. Pumped hydro storage, like I said, my personal favorite, because it is the best, and CAES. We're going to talk about what some of these other ones are. So pumped hydro is great because it stores a lot of energy. You can extract that energy very quickly, and because it stores a lot, you can actually have it last for quite some time. Here in this corner, we're almost at 41 days of storage, depending on how quickly we try to extract that energy. So pumped hydro really is great. Let's define a few of these others. Energy storage types we haven't said yet. So here we see SMES. That is superconducting magnetic energy storage. This is essentially a cryogenic, very large piece of superconducting material, and we use an electric field to store energy in the magnetic field of this large piece of material. And then we also have CAES, which is compressed air. Energy storage. So here, say you have a cave that is very well sealed underground. What we do is we've drilled down and established a pipeline, and we have some sort of a pump. And just like pumped hydro, instead of storing water at a height, we instead take air and we pump it and store it at a high pressure, which is the same. We've just generated a large potential, in this case a pressure potential. And then when we need it, we just allow that air to flow out through some sort of a turbine, which we turn, I guess it'd be a compressor, not a pump, through this turbine, and we extract that energy. So this is why it's very similar to pumped hydro. Pumped hydro is a little better because we're not dealing with a gas, but with a liquid. Okay, so kind of the idea I wanted to get across here was pumped hydro is really great. So let's learn about exactly how that works, how to model it, and how much is used right now.